Lesson: Knowledge graphs and their applications. Knowledge graphs have emerged as a pivotal tool in the realm of artificial intelligence, particularly in knowledge representation. Their ability to model real-world entities and their interrelationships provides a robust framework for organizing and utilizing vast amounts of data. This lesson delves into the functional aspects of knowledge graphs, their applications, and practical methodologies for implementing them in various professional contexts. The focus is on actionable insights, practical tools, and frameworks that practitioners in the AI field can directly apply to enhance their proficiency in managing complex datasets. Knowledge graphs are structured representations of information, where nodes represent entities and edges denote the relationships between them. This structure allows for efficient querying and inference, making knowledge graphs indispensable in diverse applications ranging from search engines to recommendation systems. A quintessential example is Google's Knowledge Graph, which enhances search results by providing users with comprehensive, contextual information about their queries. This application underscores the potential of knowledge graphs to transform how information is accessed and utilized. The construction of a knowledge graph begins with data ingestion, where raw data from various sources is collected and pre-processed. This step often involves cleaning and normalizing the data to ensure consistency. Practical tools like Apache Nifi and Talend can be instrumental in automating these data integration processes, ensuring that the data is primed for subsequent steps. Next, entity recognition and relationship extraction are performed, typically using natural language processing techniques. Frameworks such as Stanford NLP and Spacey offer robust libraries for recognizing entities and parsing relationships from text, converting unstructured data into structured triples: subject, predicate, and object. Once the data is structured, the graph is built using graph databases like Neo4j or Amazon Neptune. These databases are optimized for storing and querying large networks of interconnected data. Neo4j, for instance, utilizes a property graph model, which supports high-performance graph traversals and complex querying with its Cypher query language. This capability is crucial for professionals dealing with large-scale graphs, enabling them to perform deep analytics and derive insights efficiently. In practical applications, knowledge graphs excel in enhancing recommendation systems. For instance, e-commerce platforms can leverage knowledge graphs to provide personalized product suggestions by analyzing user preferences and behaviors. By constructing a graph that includes products, users, and interactions, the system can identify patterns and recommend items that users are likely to purchase. A case study involving Alibaba demonstrated a significant increase in recommendation accuracy and customer satisfaction after integrating a knowledge graph into their recommendation engine. Moreover, knowledge graphs play a pivotal role in natural language understanding. In virtual assistants like Siri or Alexa, knowledge graphs are used to understand and contextually interpret user queries. By mapping spoken language to a structured graph, these systems can infer the intent and provide relevant responses. This functionality is enhanced by incorporating machine learning algorithms, which continuously update the graph based on new interactions, thus improving the system's accuracy over time. Implementing a knowledge graph in a professional environment involves several critical steps. First, it is essential to define the scope and objectives of the graph. Clearly articulating what the graph is intended to achieve will guide the selection of data sources and the design of the graph structure. Next, stakeholders should establish a schema or ontology which serves as a blueprint for the graph. Ontologies like schema.org or industry-specific vocabularies offer standardized frameworks that ensure interoperability and consistency across different systems. Once the foundational elements are in place, the focus shifts to data integration and graph construction. Here, it's crucial to adopt a modular and scalable approach to accommodate future growth and changes in data sources. Leveraging cloud-based platforms like AWS or Microsoft Azure can offer scalable infrastructure and tools for managing large-scale graphs, facilitating seamless integration and real-time updates. After the graph is operational, continuous maintenance and updating are paramount to ensure its relevance and accuracy. This involves monitoring data quality, updating entities and relationships, and refining the graph based on user feedback and new data. Automated tools like GraphAware Hume or OntoText Platform can assist in maintaining and evolving the graph, providing functionalities for data monitoring, versioning, and collaborative editing. In addressing real-world challenges, knowledge graphs offer a strategic advantage in managing complex data ecosystems. For instance, in the healthcare sector, knowledge graphs can integrate disparate data sources, such as patient records, research papers, and clinical trials, to provide comprehensive insights into patient care and treatment outcomes. A study by IBM Watson Health demonstrated how knowledge graphs improved decision-making processes by enabling healthcare professionals to access a unified view of patient data, leading to more informed treatment plans and improved patient outcomes. Furthermore, knowledge graphs are instrumental in fraud detection and prevention. Financial institutions utilize knowledge graphs to map transactions, entities, and relationships, identifying suspicious patterns indicative of fraudulent activities. By applying graph analytics and machine learning models, these institutions can proactively detect and mitigate fraud, safeguarding assets and enhancing regulatory compliance. In conclusion, knowledge graphs represent a transformative approach to knowledge representation, offering unparalleled capabilities in organizing, querying, and deriving insights from complex datasets. Their applications span multiple domains, providing tangible benefits in enhancing search, personalization, and decision-making processes. By leveraging practical tools and frameworks, professionals can effectively implement knowledge graphs to address real-world challenges, driving innovation and efficiency in their respective fields. As the landscape of data continues to evolve, the strategic adoption of knowledge graphs will remain a critical component in harnessing the full potential of AI in knowledge representation.